So I watched a documentary about like information and what information is. And it was actually like really interesting. It's like it was like from like scientist, like physicist perspective. Like it's like the weird stuff where like information gets stuck on like the surface of the black hole type stuff. And but they were like, this whole concept, we use this word like information and we don't really even know what it is, or like data. But there was one interesting thing that like I saw in this documentary, and it was like, let me Google it. I need to like, it was like the person who came up with like this way to, what's it called when you like make fabric or like weave fabric binary? Does anyone know? Okay, yeah, the loom. It's like part of this documentary was talking about this thing called the loom, which I guess when you would make these like fancy tapestries, like back in the day, they took forever because maybe I just need to, this isn't the best. Like stuff like this, you want to make a tapestry or like some fabric and it has a pattern. Like this used to be like very, very time consuming. Like, because you had to like do it in a very specific way. I mean, if you like look at this, it's like the threads, it's like, is it going up or underneath or above like each thread? So, and people do this by hand, and it would just like take just, thousands of man hours to make like a pattern like this. And then I don't, is his name Jacquard Weave? What's the guy's name? Let's do the loom. The loom binary. So this guy, let's see, yeah, Joseph Marie Jacquard. So he kind of developed this machine that used like punch cards that, could tell, it was like a loom. Does anyone know what a loom is? It's like it's a thing that makes fabric.
Yeah.
So, like he created this system where like, he had these punch cards, and then this would tell like the loom to like, move the threads up or down, and then they could throw in the other thread, because it's like kind of like this. Yeah, one's going like that way and this way. And so he created this machine using punch cards that would like automatically like lift up the threads to be their right position. And so in these punch cards, it's like, oh, this just tells how to make that pattern. And then you for different patterns, you'd have different set of punch cards. And like, yeah, you can see here's, you can make, with this system, you could make like essentially any pattern. There's like a weave with like, actually, this might even be it. Like, this is a tapestry with like this guy who made this thing. Like, this is actually like a piece of fabric right here with him on it. So you can, he kind of figured out you could encode the information to weave stuff, on punch cards. And then that punch card could be hooked up to a machine that, would tell like the fabric to either go like up or down. And then that's how you could create the designs. And like, when this was like back in, when was it? 1804. I mean, this is a computer. right? Like this is a like this is a programming language right here. What do what do these dots kind of look like? It's like you can either have dots or you don't have dots.
Ones and zeros.
Yeah, it's just like that's just binary right there. And in this case, like the dot or not having a dot is, this idea of like the string either goes up or the string either goes down. And then for each piece, like each card is going to be like, it lifts up the threads and then you throw in the new piece of string and then you go to the next one. You lift up the threads in the right order and then you throw in the string. And then with like the different variations, you can, create crazy patterns, such as like a drawing of the guy himself. And then you could, there's probably a lot of work in creating these cards, but what's the benefit once you create this, like these cards, which would probably be pretty long to create like a pattern. But the benefit is like once you have this card, then you can like throw that in a machine and then you can just reuse it. So this might have taken some time to create these cards, but then they were reusable, and then you could throw those into like the loom, who could then do it like super fast.
So this is like the grandfather of coding, like the first coder, kind of.
I don't know. Like they usually give like the father of coding, like of computers, to Alan Turing. He kind of gets that kind of prestige. But yeah, this is very much, kind of that you like a specific computer. I think Alan Turing gets more credit because he did a lot more of the math that like describes what computers could do. But yeah, this is really just, a pretty ingenious, like very, very specific use case computer. So it's like when we talk about like data and information, it's like, what are all these zeros and ones? Well, it kind of depends on like the context of them. And in these, like the zeros and the ones correspond to like whether or not like the thread should go up or down for like each given, weave. And like everything it like can, like I don't think there's anything that you cannot convert to like 0 and 1 logic. Like those are like the fundamental units of information. They're called bits. So you can take something that's like seemingly complicated as like a movie, and you can convert those into like zeros and ones. And I'll do that, like you can have like a 8K video, but really behind the scenes it's just zeros and ones. It's going to be a lot of zeros and ones and a lot of cards, like, but nonetheless you could say like, hey, this combination of zeros and ones, this will tell a pixel on your computer screen to go green. This one would tell a pixel on your computer screen to go yellow. Or like you could arrange these so this could be like a sound wave. Like, as you're going through these, it's kind of just plotting the position of a sound wave. Or this could be the letter E and this, or this could be like the letter H, and this could be the letter E, and this could be the letter L. You could spell out hello. So we can use these zeros and ones, and like with a system, that tells it how to read it. So it's pretty cool stuff. Maybe I would say, yeah, if you're interested, just like maybe just on your own time. I won't get into it. You can Google this guy, watch a little show about it.
Yeah, binary still just makes no sense to me. It's so hard to like even comprehend.
Binary is the simplest thing ever. It's like, so first of all,
But it's like, how does that work? Like, I mean, I get the concept of it, but like, it's just zeros and ones.
yeah,
Maybe I'm
I-
overthinking it. I don't know.
I think this, like, I'm not going to explain the loom because I know, like, I know binary, like I've done like some computer architecture and like have built out like tiny miniature computers. When I saw this, when I was like watching the documentary and I saw like they were saying how like the thread just had to go up or down, and then they showed me this punch card. It was like, oh, I like instantly got it. But I kind of had that background in binary, but really, and what I'm going to try to like just briefly talk about before we get into databases is binary and like how this is like, I think the complicated thing is, so let's just like this punch card right here. Like, what does that mean? I mean, it depends on like the program using it and like how the program reads it. Like we could throw this, and this is why like data types matter at the end of the day. Like this is why like the computer needs to know, hey, this is a number, or this is a string, or this is an array, stuff like that. Because if this is a number data type, then the computer is going to like treat it as a number, and then the binary means something different when it's the data type number. But this card could also be an instruction on how to, like, the data type could be like the thread position for a loom. And then that's totally something different. And so this is like, oh, the first thread goes up, then the next 8 threads go down, then the next 2 threads go up, etc.
Yeah, that makes sense.
So it's, I would what this is a good like when you kind of watch how like this works, this loom, you could then you can kind of see it's kind of like since it's like a basic use case of a computer, that might help make it more sense. But another thing that might make more sense or help make more sense is actually talking about binary and what it is. Have we done this yet? Have I taught you binary?
No, but I'd like to know why it's just 1 and 0. Why can't it be, 0 to 9?
I've also
Isn't it
heard
like an on and off switch? You'll flip on and off.
I've also heard it explained as like that's also how Braille works, how people read Braille, like those patterns of up and down bumps. That's also kind of binary.
Yeah. So so first of all, why 0 and 1? Well, I'll ask you this: why 0 through 9? I think that's a better question.
Wouldn't that give you more possible outcomes, more,
Well, why not? If that's your reasoning, why don't you do 0 through like, I don't know. There's a random number right there.
because it seems like if you're only going left or right, if you could just turn in part amounts, you get smaller and more accurate bits out of it. You know what I mean? Like if you could turn to 45 degrees instead of just straight ahead, or 90 to the left, 90 to the right, you think you'd be able to get more.
Well, I can create any number with this that I could with this. There's other numbers. So yeah, why 0 through 9? This one like blew my mind when someone first like actually made me think about this. Why don't we do 0 through 5? Or like I said, there's this one like 0 through F. What like F is, let's pretend F is a number. Do you get what I'm asking? Like, why is our number system 0 through 9?
I don't know.
So a simple set of numbers can be mixed and matched to make bigger numbers.
I can do that with 0 and 1. I can do that with
I feel
0
like
and
it just can't get more simple.
0 and 1's like, that's
It's
the
like-
simplest. You can't,
That's yeah.
Numbering systems also just used to be to 12, or it was there to 12.
yeah, why not 0 to 12?
Someone just wanted to do 9 and everyone agreed to it.
I think that makes sense to have like 2 different values. Right, 'cause it's just like on or off in a way.
The point here was 0. There's no reason. The best reason you could probably come up with why this is why usually someone gets this. Why do you think there's 10 numbers in our system?
Because someone likes the number 10. Or they did, well, because it was 12 before and then someone changed it to 10. I don't remember why. I remember hearing that though.
Probably, I don't know. The
1 and
best
0.
the best reason I've heard is that we have 10 fingers. Like that, I don't know. There's no real reason we like.
I remember hearing someone say why it went from 12 to 10 though. Like it used to be 12.
There might, it's kind of crazy that we actually, that I don't think this is kind of crazy. Like there might, yeah, if there's, I would expect there to maybe be more number systems out there. Like
That's a good point.
it's kind of the same as like everyone just kind of randomly agreed to use the same alphabet. Like, wouldn't that be crazy? You go to like China and they're using like A, B, C, D, E, F, G. Alphabets are a little like obviously different, but it's kind of the same thing. So yeah, it's
I
just,
think a numeric system would be easier to convert. It's like you can only have so many variations of that.
I can make any number with 0 and 1 that I can make with 0 and through 9. There's also, when you do CSS and you're typing out like F 0 0, like what is that?
That's like a color's specific number that it gave, so you can use it.
It's a color. I mean, it like maps to a color, but what is this? This is a number. This is a number you can like do math on. I could add 1 to this. But who knows what number this is? Anyone?
Well, FF would be 255 because it's full color.
Yeah, this is 255 times 0.
0.
This is a big number because, well, this is 255 right here. But, and then we'll talk that this is a huge number. I would have to get a calculator. So this is hexadecimal. It's a number system that uses 15 numbers. So you count from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, well, we run out of numbers at 10. So let's just use the alphabet for the rest of the numbers. So A is 10, B is 11, C is 12, and so forth. And F is 15. So I can do, yeah, let's convert FF000 FF. Let's convert that to decimal. See, FF00 FF is really just 1,600,000. Like those are the same mathematically. They're just in different number systems. And then I can convert that to binary. That's 16 million in binary. Oh, I'm not sharing my screen. I'm on my whiteboard. Sorry. I need to show this. Probably just saw me do that magically. So I took this hexadecimal number FF00FF, converted it to decimal using a calculator. So there it is, 16 million. Like I said, it was a big number. And then here it is in binary. This number right here is 16,700,000, 11,935.
So there's millions of code for everything on the computer and it's just in 0 and 1 categories.
So let's not think about code right now. We're just talking about numbers. This is just numbers. So no code, just numbers. We'll get into like code in a second, but so let's learn binary really quick. So, well, let's start out with, our number system. Like, once again, this like blew my mind, like how little I knew about like something I used every day. I was like, you just take it for granted just because it's all you've ever known. It's like one of those things where you realize how like ignorant you are about something. Okay. So here I'm counting from 1, 2, 3, 4, 5, 6, 7, 8, 9, and we have these 10 numbers. So this is why like some people, when you start counting, you maybe say, hey, I'm going to start counting from 0 because these are my 10 numbers I have. So what happens when I'm trying to count and I run out of numbers? What do? I need to do 10.
Put them together.
You
I start-
basically restart from the beginning.
Start putting them together. And what happens is, this becomes my ones place. And this becomes my tens place. I mean, I guess we did learn this in like what, first grade? I don't remember when I learned this, but it was pretty early on. So how you could say this is I have 0 ones and 1 10. And that gives me 10, right? If I add another one, that's really my hundreds place, right? We just know this so intuitively, we don't have to do this. But here I have 1, 100, 110, and 0, 1. So that's 110. If I come in here and put a 3 and a 0 and a 4, I have 4 ones, 0 10s, and 3 100s, right? So let's do that with binary. So now I only have 2 numbers, 0 and 1. So I'm counting. Okay, so now how do I do 2?
1 1
It's going to be 1 0
0. Oh,
because, and now this is my 1 spot. What spot would this be?
tens. No,
It's not.
Your
It's my
twos.
2s. So I have 1 2 and 0 1. So yeah, this equals 2. Here I have 1 1 and 1 2. That equals 3. All right. So now once again, I'm out of numbers. So I do 1 0 0. Now this becomes my 4 spot. So I have 1 4 and 0 2s and 0 1s. So that's 4. And you can start to maybe see 1 2 4. This is going to be like n squared. With our system, it's just, we just add a 0. It's kind of like just too intuitive. We have the 10s, 100s, thousands, 10,000s, 100,000s. But with binary, we just kind of double it, 16. So it's 2 4 6 8 32nd. Like that's how many of the things we have. So if I have like 1 0 0 1 0 1, what number is that?
37.
37, yeah. Because I have 1 1 1 5 132. So that's 37. And yeah, hexadecimal is you go 1 dot 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 dot, you get to 9. And then yeah, you'd say, let's just make A 10, B, C, D, O, E to E,
Wait, CE.
D, E, F. Where, you know, F is really like, it's 15. A is 10, 10, 11, 12, 13, 14, 15. So when I do like hexadecimal, you know, like that's an A. This is like how many 15s I have. And so I'm going to times it by 15, which is, so then this is like how many 255s I have. And then this would be like 15 times 15 times 15. I don't know what that number is. Calculator. So that's just how many 15s I have. And then I can times that by 15. So this, no, that should be 255. What am I doing wrong here? I'm doing the math wrong somehow. I kind of forgot how to convert. Because this does become your 255 spot. Is it 2 to the 5th? Is it 16 times 16? That's close. It's maybe it's that -1. I don't know. I'd have to like review how to come up with this, but it's kind of the same idea where like, you know, this would be how many 15s we have. This is how many 255s we have. I don't know what this would be. Probably something like 4,000. This would be like our 4,000 spot. The point is like, we're using like, you can have different number systems that use different numbers. We use decimal just because it's like the standard, but yeah, computers use binary. So why do computers use binary?
On and off.
Yeah, it's all about like electricity, like, you know, underneath like the hood of your like computer, there's like transistors and they like can be like on, I don't know, or off. It's all about like connecting power. So they can have two positions of like power or like no power. There's your light turning on. No light. Anyway. And like also like the bit is like, it is like when like you're talking about information, it is like the most simplified way you can store, like you can have data. So it is like, it's the fundamental unit of data, not in just computer science, but like in like physics, the bit is the most basic unit of information. Because this is the mind, like with 0 and 1, you can do like anything. You just need to know, like you need on or off. So it's kind of crazy. But I think another like interesting, maybe like information system you could think of would be like DNA. Where what does DNA have, like A, T, C, G?
Yeah, it's got 4.
So that would have 4. But you know, like, so it's kind of like it has like 4 letters or like 4, these could be numbers, or I mean, they're technically molecules, but like with 4, you know, 4 numbers or 4, you know, units, you can create all the life out there. So you know, it just goes to show, you know, you can like, with just some basic units of information, you can do a whole bunch of crap. So you don't need, yeah, that a lot of these two are enough. You could actually like probably mathematically convert all this stuff to 0 and 1. But anyway, so y'all know binary now, right? What number is this? Let's just do the last little quiz.
Oh. 10.
Yeah, that's 10. Cool. But that's just the number part. So now we got it. So that could have nothing to do with computers. Just like now, you know, we could do math on this, but let's kind of maybe go now and talk about the data part about this. Where is it? I have it up here. So we'll get back to like the SQL part, but something when we talk about data, and this is kind of like go back to maybe that punch card diagram, like it's just like a whole bunch of, or like, yeah, someone's brought up Braille, like just either there's pokey holes or not in certain orders. Like it's all kind of the context of like what that is. So when we go to like databases, we're going to see like a whole bunch of data types. So let's kind of maybe think about like, why are there so many different data types? Like, here's a big int. This is a signed 8-byte integer. Then there's a integer signed 4-byte integer. It's like, wait, what? Why do we have 2 integer types? I'm like, what's a byte? What's this sign stuff? Like there's double precision, float. So we've seen float, right, with Ruby. So a float is, there's actually a couple different kinds of floats. There's like a double precision floating point number that's 8 bytes. There's a single precision floating point number that's 4 bytes. Oh, here's another int, a small int, 2-byte, small serial. So there's all these different kinds of data. So yeah, what does all this mean? Like, just kind of at a high level. First of all, let's just get some terminology clear. So does everyone know the difference between a bit and a byte? The bit, so the bit is the smallest unit. So that's the 0 or 1.
Yeah.
A byte is 8 bits. Why? I don't know if there's, I don't know if there's a specific reason why it's 8. I don't think there is.
I remember hearing why when like computers were first coming out and they had like the computer learning classes. I remember hearing a reason. I think.
You'll also see you'll see a lot of like with computer stuff with like these numbers. There's a lot of numbers that kind of follow that like n squared. So it'd be like, you know, 1, 2, 4, 8, 16, 32, 64, 128. So you will kind of see numbers within like those value, one of those values. That's pretty common. So that's probably one of the reasons. And yeah, it's probably 8 bytes was probably like one of the first earliest compute like units when they were like starting to like write computers. But anyway, a byte is just 8 bits. So how many bits is 4 bytes?
I just got confused.
Okay, so
I was trying
so-
to remember that. I think the 8 thing was that's how many things could fit on the card at the time, like how many like could fit on the thing. I'm
You
like,
asked how many bits is 4 bytes,
Yeah,
so it'd be 8 times 4.
yes, yeah, exactly. It's 8 times
Oh.
because there's 8 bits to a byte. So yeah, so we say 4 bytes, that would be 32 bits.
So this is why they call it like gigabytes.
yeah.
Yeah. Actually, I
and
think those,
terabytes.
those are like
Giga is like 100 bytes.
gig is like,
100.
it's like a
1,000.
billion. A gig is a lot. A gigabyte's like a million billion bytes or something. It's a lot. So yeah, let's go back. I want to go back to like the whiteboard. I think this is like just a little interesting to think about. So why do we have all these different like for like integers? Why do we have all these different like 4 bytes or 8 bytes or like 16 bytes? Well, let's think about it. If I have and just to keep my drawing simple, I'm just going to use bits. Let's say I have 4 bits. All right. Oh yeah, thank you. Yeah, 1 gigabyte is 8 to the 9 bytes. That's 88 billion. I don't know. Okay, anyway, sorry. Let's say I have 4 bits. And when we're talking about data, we're kind of talking about, so I like this visual of the Loom punch card. So we can like see it. Now, something when we're working with like these data, it's like, notice how these punch cards could be thought of as like a type of data. Like this could be a data type of like how to like weave a given string, like a given like thread. Do you notice something about these cards, how they're like the same size? Like they're all going to be like whatever this would be, like 4 by 12. And they all potentially have like the same amount of potential places you could poke a hole or not. Does that make sense how they're like, where the holes are poked are different, but they all have like the options to poke the holes? Is that making sense?
It's
Yes.
a little confusing to me.
Like we don't, so these are all cards, like the cards are the same size. There's not like a card that is like 4 times as big as the other one. Right? There's not one that's like half the size. They're all the same size. Does that make sense? Where the holes are poked might be different, but they're all the same size. So how, oh wait, I'm not even showing the card. Stupid screen share, sorry.
I was so confused.
Sorry, when I do the whiteboard, it like only shares the whiteboard. Okay, sorry. Okay, so when we look at the cards, see how they're like the same. Here's one card, and then here's another card. They're the same size, and they would have the same amount of potential places I could poke a hole, right? I don't see a card that's like 4 times the size as this. This is like very important with like data.
Yeah, now it makes more sense seeing it like that.
Like here's some cards. Like here's a card. Just ignore these 2 dots. Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this card would be a 10-bit card. Okay, let's say we have this 10-bit card.
So is that kind of like saying how the holes would be like 1, maybe 0, and then no hole would be the other? So hole would be 1, no hole would be 0.
Yeah. Yeah. So
Yes, that
yeah,
makes sense.
exactly. Like let's say a hole is 1 and no hole is 0.
Okay. So even if one card has more holes, it's not storing more data.
Yeah. So yeah, let's just go to this example. Because let's say like I have now a loom system that uses, it's a 10-bit system. So each of my cards, and I'm going to draw this out as like just in order. So we have a 10-bit system. 1, 2, 3, 4, 5, 6, 7, 8. Is that wait? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, there's my card. So what I could ask you on a 10-bit system, first of all, it's kind of like it's like what we kind of get to is like how many combinations can I make? So one way you could think about this is, first of all, what's the lowest number that your system could represent? Be 0, right?
0.
Yeah, all of these would be 0. ... So you could have a card with all zeros. And then you can kind of visualize this, I could just go through each card and like do a 1, and then that would be an option, and then 1, 0, and then 1, 1. So like I could count, and this is where counting is nice. It's just like the same as counting, like how many combinations do I have? Well, it's essentially just asking what's the biggest number I could do. Because that's going to be how many combinations I could have. So what that would just be all ones, right? 1, 1, 1, 1. So I could count from 0 to 1, 1, 1. I believe that's just like 2 to the 10. Anyone know what 2 to the 10 is? Probably 2 to the 10 minus 1, I think. 2. Where's my 2 to the 2, 10? What is that? Okay, yeah. So this would be, I could count up to like 1, 2, 3. So with a 10-bit system, I could, there's like 1,000, 224 possibilities of combinations. And I could then say, hey, I could then choose the system I want. I could say, hey, I want these to be numbers. So if I have a 10-bit system, what's the highest I can count to? That's kind of like the essence of this. How high can I count if I have a 10-bit system? I can only count up to 1,023, right? Because that's this going to be full. Does that kind of make sense?
Does that make sense?
Now, yeah, these could be numbers. I could say these are numbers, but I could also have these be like instructions on the loom to whether lift up the thread or not. So then that way, in that sense, I could have 1,000, 24, because the zeros included, combinations of thread positions I could have if I had a 10-bit loom system. You know, these could be like colors, like how many colors could I have? Because I could, you know, instead of, it's, you know, even though it's zeros and ones, I could like map these to colors. And that's what we do on computers. I could map these to colors. So then I could have if I had a 10-bit computer or like this 10-bit possibility of colors, this is how many colors I could have. And, you know, you see that with like when Nintendo first came out, it was like what? I think it was like an 8-bit kind of machine. So you could have 250, like, and so 8 bits, how many possibilities are there with 8 bits? Well, it's 2 to the 8, which is 256. So that's how many colors you could have with an 8-bit system. And that's why when you like play like the original Mario, it's like, you know, it's, you know, there's not that much detail in the color.
Oh, is it? Oh, never mind.
Does that, or like and that's why like, you know, you could have 8 bits to represent sound. So that's why like when you go play Mario, it's very like, the sound is very distorted. It's like, they call it like there's actually like in music software today, there's like bit crushers, which can give you that like Nintendo sound. And it's really just like, it's called a bit crusher because it's like making the bits available to you smaller, which is kind of funny, but you can get cool sounds with that. So yeah. So if we have, but now with hexadecimal and like when we do CSS, we see like like how high we can count up to with decimal is F, 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 F. I believe this is a 24-bit system. So let's see, 2 to the 24. How many colors can we do? Yeah. That is 16 million colors. So with hexadecimal, like with what we use in like CSS, we have like, you know, this combination. We can count up to 16 million. Like, is that not crazy? You can have, think about your Nintendo back. I don't know if I'm probably the oldest one here, obviously, but when you like that first Nintendo, you could have 256 colors total. Now you can have 16 million colors. So you can start counting at 0, 0, 0, 0, 0. Like this would take a very long time, right? And then I could go 0, 0, 0, 0, 1. Like that would be a different color on a computer. And I could count all the way up to where this is F, 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 F. And that would be like counting to 16 million. Why does anyone, any ideas? Why is, or does anyone know, like when you're, even with CSS, like what are these numbers referring to? Like why is it like, you know, 6 Fs? Like why 24 bits?
It's Roy G. Biv, right?
Yeah. What were to happen if you were to look at your computer screen, like
It's red, green, blue.
yeah. If you were to look at like the pixels, you would see there's 3 lights. There's a red light, there's a blue light, and there's a green light. I need to like stop sharing. Let's just look at this. Or do I have a picture of this on here? I think it's good just to actually, seeing is believing. I mean, you can like try to like yeah, like if you were to like look really, really close at your computer screen, this is what, and you would see this. So one combination of like one red, one green, one blue,
You're
those
not
are,
sharing your screen.
damn it, thank you. Sorry. So one combination of red, green, blue, that is a pixel. One of those three, like that's one pixel. I don't know how many pixels does like a new Mac have? It's like they're crazy small. So there's like millions of these on your computer. How many pixels?
It depends on the size, but
The net 2000 by that was 227 pixels per inch. I think it's just that. It's just whatever 19 to 20 times 1080 is, right? So it's a
that's
lot.
just camera resolution.
Well, it says that the 27 whatever type per inch, and then it's 13 inches. 227 times 13.
No, it's just 2,560 times 1,600. Because that's width times height.
So it's a lot of pixels. I mean, they call it retina display. They say it's at a level where like if you're at a certain distance, like they can't really make it, like making the pixel smaller is not going to make the resolution better. It's kind of the same thing with the colors where like
It's
It is like-
4,096,000.
4 million pixels. Okay, yeah, that's a lot. So you have 4 million pixels, each have like 3 little colors. And each of those 3 little colors, you can have 16 million different combinations. And then you can get a nice screen. So yeah, the visual on like can like high def screens and like with colors, it's like it is getting, and this is what retina display kind of is saying. It's like it's at a point where like they can't really make it. If they go like smaller or make, you know, the system to have more colors, you're not going to notice the difference. Like, do you think you can distinguish between 16 million different colors? People say they like that. They say like that's where the human eye can stop, like can't really distinguish. And I'm like, whatever. There's someone who can distinguish 16 million different colors out there. That sounds crazy. But anyway. So yeah, with hexadecimal, how hex and with colors in particular.
This the human eye can distinguish 1 million colors. 1 million, it says on here.
Yeah, this is this would say 16. Because I can make 16 million different colors on a computer screen. But anyway, like if a human eye can only distinguish 1 million, then why would they use, then this would be wasting storage. But even if it's 1 million, 16 million, whatever, that's a lot. But let's look at how like kind of going back to like the example of, well, what does this mean? So FFFFF, this could be a number. I could think of this as being 16 million, whatever. I could also think of this as being an instruction on a loom to raise the threads. Or I could also think of this as an instruction to tell a pixel on how bright to light up the pixels. And that's what we do with colors. This is the R value, this is the G value, and this is the B value. So this the information will tell how bright to make the red pixel, how bright to make the green pixel, and how bright to make the blue pixel. So if it's FF, that's 255, that says, hey, go full red, go full green, and go full blue. Does anyone know what color that is? Or what that would look like if you had a whole bunch of
White.
pixels? What?
Is it white?
Yeah, that's white. So right here in where you see the white backdrop, there's just millions of pixels that, you know, are full red, green, and blue. If it was 0, 0, 0, what would that be? If it's all zeros?
Black.
Yeah, that's black. What if it's like, I don't know, let's do like halfway, 9, 9. What if it's all nines?
That'd be gray.
Yeah, that's gray. And then, yeah, what if it's like 9, 9, 0, 0, 0, 0?
Probably be like a pinkish red.
Yeah, it's like, it's not a full red, so that would probably be like pink. And then, yeah, what is 1, 2, 3, 4, 5, 6? Who knows? But that's like, if you looked at it, the red would have a very low value, but there'd be a little red, there'd be a little more green, and a little blue. That'd probably be like a darker color, just because they're not that, none of them are that bright.
Ish.
And you can go like, but so does the point where like this FFFF could be, it could be a number, or it could be, the computer could say, hey, this is either a number and I can do math on it, or I need to tell the computer, hey, this is actually an instruction on how to light up your screen. Or it could be an instruction on, you know, how to create a part of a sound wave. So when we go back and look at, you know, we kind of look at this visually. So yeah, here's kind of like, you know, if we have all zeros, that's black, if that's full red, stuff like this. It's kind of crazy that yellow is, there's really no yellow on the screen. It's just red and green. Like if I were to go zoom on this yellow part right here on my screen, it would just be red and green. So let's look at the number part. So like, why do we have so many different storages for numbers? Well, the more bits we have, the bigger the number we can store. So if we want to, and also if we want to store a decimal number, there's maybe different ways, different strategies to do this, because it's like, how do we store a decimal number? And one of the most common ways is what's called floating precision. So once again, this uses a 4-byte system, 32 bits. And then people have just decided, who designed this system, hey, the 23 bits on the end are going to be reserved for the fraction, like fraction information. And then the next 8 bits are going to be reserved for like the exponent. So, and then the next one is going to be the sign. What do you think the sign is? If the number's positive or negative. So I'm using 8 bits for the exponent. So that's going to give me 2 to the 8 possibilities. So that gives me, you know, 256 or whatever. You break that up in half. So my exponent can be as small as to the minus 126 and go all the way up to the 127th power. And since I have a sign, I can do positive and negative numbers. And then the remaining 23 bits I can use for the decimal or for the fraction part of it. But there's going to be like, I can't represent, like with 4 bytes, you kind of see how there's no way I can represent all of these numbers from 1 plus 2 to the negative 20 through all the way up to 2 to the 127th. Those are huge numbers. How many numbers can I represent with 32 bits? Well, it's about 4.3 billion values. How many decimal numbers are there from, I don't know. You could just say, how many decimal numbers are there from 0 to 1? There's infinite. So what I have is I have to kind of step, there's going to be a lot of missing values. So there's going to be like these gaps. I'm not going to be it can't be 100% precise. Because I'm trying to represent an infinite amount of numbers. And I only have 4.3 billion values to do that. So a good way to think about this is like with a clock, you could have like the analog clock that has like the second hand that is actually going through and telling you exactly infinitely what time it is because it's analog. Or you could have a digital clock where it counts the seconds. Now in between like 1 and 2 seconds, there's like, you could break that up into infinitely small, like milliseconds, microseconds, but we just get the second data. And usually that's good enough, like 4.3 billion values is good. If we need to, like, say we're like launching a rocket ship and we want more data, we want to be more accurate, more precise, we just use more bits to represent our number. So we can do something that's called double point floating precision, where we use 8 bytes instead of 4 bytes. So that gives us 64 bits. That should be 2 to the 64 combinations. So this gives us, if we double the bits, then we get, I don't even know what number that is. Quadrillion, 18 quadrillion possible values. So if we have 64 bits, we can count up to that number. So why don't we just use, like, for numbers, why don't we just go ahead and use, like, well, why even use 8 bits? Why don't we use like 120 bits for each number? Because then we could just be really accurate and like have so many different possibilities. Why would we maybe choose 4 bytes over 8 bytes, even though this is going to be less accurate?
Takes up less space.
Yeah, it's going to take up less space. And you could think of like, these punch cards, because they only have 10 bits, I could make these like, these could be like really small and I could really compact these in my database. But I can only count up to 1,000 with this system. If I go and use, I don't know how many are on here, but there looks like there's a lot of bits on here, right? So these actually might be separated, but anyway, that looks like that's like 128 bits or something on that. So I could represent a whole bunch of data on one of these cards because there's a lot more options, but they take up more space. They're bigger. So there's the trade-off. So if I never really expected, if I don't need the precision, then I wouldn't use it. Another thing we can look at just with looking at bits, I think is interesting just because I'm a music guy. is sound. So once again, sound is like, if we look at a sound wave, it's once again, it's an analog, meaning there's like infinitely many points in this sound wave. But computers, we can't have infinitely many points because we are always going to have a limit with how much data we can store, how much information we can store. So how we do sound is we take a sample of the sound every so often. That is the sample rate. So maybe every, millisecond, I take a sample and I see, hey, where is the wave? So that's this direction, the sample rate. And then I also have the concept of a bit depth. So I could have a small bit depth, and then that way I can't really be that accurate when I do place the sound wave. So this would be an example. So here's the sound wave. This would be something that has a small bit depth. So we're not using that many bits to point to mark the sound. And then we also have a small sample rate. So we're not sampling often. And we get this very stare looking sound wave. And this would sound very distorted. But what we can do is we can take more samples, and we can also increase our bit depth so we're more accurate on where we're actually placing it. And then we see we get a little closer to the sound wave. And then we can get higher and more to the point where, even though this would be, if I zoomed in, it would look like this. It starts to look very much like a sound wave. And that's how, we can store sound. And obviously this is going to maybe get a little bigger. This is why when you go download a song, it's going to be maybe, I don't know, a couple megabytes. Because you're sampling, for each 4-minute song, they actually sample, the standard rate is to sample it's 44,000 samples per second. And then there's a 16-bit depth. So that's 44 samples a second with 16 bits. That's a lot of data, right? So that's why when you download a song, it's a couple megabytes or something. Or obviously probably the biggest is videos. Think of videos are crazy, especially if you get into 4K. That's where you start taking up gigabits of information. Let's talk about RAM. So what's the difference between RAM and storage?
RAM is your random access memory. So it's basically just holding it for the time being, like your browsers when they're open. Whereas storage is that's where you're actually storing, say your music or your videos or a game or something.
Yeah.
That's where you can have it stored so you can go back to it later. Whereas random access memory is kind of just in the second when you're using it then. Does that make sense?
So yeah, I like to RAM's the memory that you have that's while your program's running or while your computer's on. Storage is just that while it's off.
Yeah.
Something that just blows my mind, I'll try to find maybe during break a visualization of this. But so 32-bit systems are kind of gone, or they're becoming less a thing. So if you have a 32-bit system, you can only have up to 4 gigs of RAM. You just run out of memory addresses at that point. With a 64-bit system, which your computer most likely has, you can have, once again, and we saw this difference when we're looking at integers. It's how high can you count up to? With 32 bits, you can count up to about 4 billion. With 64, 2 to the 64, you can count up to 18 quintillion. So 64-bit systems we can have, this is the limit of RAM we can have. I don't think we're going to hit that ever. That's a lot of RAM. But something that's really interesting, a 64-bit system is you're sending instructions through a computer at only like 64 bits. Like that's how long you're like the processor, that's as big as the processor can get instructions is, and 64 bits is not that much, right? Like that's, you can like visualize 64 bits. Like I could draw that out. I mean, it's right here. There's 64 bits. So when you write code or like when your computer runs, you're sending it 64 bits at a time. It's kind of like the punch cards. Like your computer's getting fed 64 bits of these, like the punch cards would only be 64 bits. And you could kind of just assume those are like in line and it's just getting fed to your processor. Like that's, in my mind, that's tiny because, you know, there's obviously things that are much bigger, like when you talk about videos and that kind of stuff, but it just goes to show how fast your processor is. Because your processor, when you look at like processing speeds, oh, does it not say? It's like gigahertz, right? 0.4 gigahertz.
Yeah, it's gigahertz.
So gigahertz is, it's like a clock. You can think of it kind of like as a clock on your computer, like how many instructions per second can you send to your computer? And it's like the clock rate. So it's 2.4 gigahertz. And we saw that a gigahertz is what, a billion? So it's like 2.4 billion. It can handle 2.4 billion instructions per second. So that's how your computer runs. It's just, it's insanely fast. So you could just think about like these cards going through your processor at, you know, 2 billion a second. So they're small cards, but they go through very fast. And then you might have like 8 processors. So you might have 8 separate machines. And yeah, it's really, it's kind of cool, but and then one more thing, and then we'll take a break. I just want to talk about compression. And if you watch Silicon Valley, this is like their algorithm is like the whole idea behind their like unicorn app is they have an amazing compression algorithm.
I just binge watched that whole show. So good.
It's pretty good. It's a good one. And like, we'll see now, like, so a compression algorithm, like what is that? Like, why would that be so important? Well, compression is very important and it kind of relates, it does definitely relate to data. That's why I'm bringing it up. So there's a way to take like some data and we can compress it. And what compressing means is like, let's say we have a photo and it takes up this many like megabytes, this blue area. We can actually compress it and make it smaller. It's not going to look like a picture anymore. It's going to be like gibberish, but we can compress it and then we can actually convert it back to the original. And why we would want to compress it is because maybe we want to store it somewhere so it's less storage, or we want to send it over the internet. So it's less we have to store. And then on the other side, they can uncompress it and get back the photo. So it's a very useful thing, right? It's kind of the way we can get rid of some of this unused data. We can compress it, send it, and unpackage it and get back the same thing.
That kind of the same process as a zip file, or is that different?
Yeah, that's what a zip file is doing. Like with the zip file,
Okay.
you're taking it, and then you're compressing it. So yeah, you can't read, like when you compress it, it's totally like, it's no longer like you could never read it, but it has the information to get back. So there's two types of compression. There's a lossless compression. So lossless compression is you convert it to this smaller form, and then you can get back the exact same thing. So you can, as many times as you want, you can compress it and get back the same thing. There's also lossy compression where you can compress it, but when you uncompress it, you don't quite get back the same thing. It's maybe a little distorted, like some of the information has been lost. So if you do this, usually it's not that much though, and so it's fine. But the problem becomes when you do this over and over and over again, then you would eventually end up with something totally different. The benefit with lossy compression is you can generally, or totally, you can compress it more. So this is good for things like photos and movies. Like if you're just streaming something, or you're just sending like a photo to like a website, like one time or a couple times, like Netflix, they probably have their database where they want their original, whatever 4 terabyte movie that's 8K. And then when they send it to you, they might compress it. And it loses some of that information, but they can send it in a smaller file and then you get it back. It's not as clean, but who cares? Or like, they send you a photo. It's not the same, but your eye can't tell. So that's compression.
So how do you control that? Like if you don't want compression loss?
There's different like algorithms that would say, hey, this is a lossless compression or this is a lossy one. So you would just choose the one you wanted.
And other than just sending in a smaller package, is there a reason to have lossy? Or is it just so it's smaller when you're sending it across?
Yeah, that would, yeah, if lossless was as good as lossy, we wouldn't use this, but there's like math theorems that are like, this could never be as good as this.
So is lossy used a lot more then?
Actually, I don't know. I would say so if you're doing something like a zip file, do you think that's going to be lossy or lossless? Like your homework, like your
Lossy?
oh, that better be lossless. If that's lossy, like if you have your
You'd
code,
be losing some information, right?
yeah, that would break your code.
Okay.
Probably, yeah, that would definitely, like, if you change 1 0 to a 1 in your code, it could break your whole app, right? Could have it change it, that'd be like a syntax error. So there's definitely stuff like you can't lose any, like you send like 2 quadrillion bits, they better be the exact same. Because
So then with like pictures or videos or audio files with lossy compression, are they just losing just like quality? Like
Yeah.
how does it know what it's losing? You know what I'm asking?
I mean, it's going to be random a little, how like it's not the point. Like with lossy, it's like if you did it over and over and over again, it would, like if it was a picture, it would just eventually it would blur.
Right.
Like, I don't know,
okay.
like the algorithm would probably, like which algorithm you used would like blur it differently. Probably be pretty cool to like go through different lossy compression algorithms and see how it like blurs it over time. But
Okay.
and it also gets into like, I have a friend who does like, video stuff, and like videos have different algorithms because like he could say, you know, you're watching a video and then there's just like this huge section of like a shot that's just, you know, it's essentially just blue. You don't want to use like 4K, like, I don't, you've probably seen it when you're watching Netflix and it like gets a little like squarey at like a part. So there's all these different algorithms for different types of data. And even for different types of like scenarios of like a shot. So
Okay, I think I know what you're talking about. Like if they're passing a wall on a show that's blue, rather than having 16 million blues, they cut it down. So then you kind of see a block of 3 different blues.
yeah. So they're like, oh, there might be like, as far as like the like actual data, there might be like, you know, 300,000 different blues in this blue, but it's like, you know, we can just really treat this as like 20 different blues and the user's not really going to notice. So
Okay,
we lose some of that, or we're going to lose some of that data, but we're going to be able to compress that a whole bunch. Sweet. Yeah, I know we haven't really, I think like the database stuff, like the SQL stuff today, you're going to learn more about it with your homework. We'll definitely go through a demo when we get back, but let's take a break. And then when we do get back, we will step into SQL. But I like, this is a very high level like introduction to like almost this class in, if you're like taking a college class, this would be like computer architecture. It's like really learning how the data stored. For me, it was a very interesting class. I don't know, maybe not super like applicable to like for what I do in the real world, but it's still interesting. And some of this stuff is kind of, it's kind of good to like, at least at a high level, know what this is about. So, and it's kind of fun to nerd out on. So, but anyway, let's take a break. Let's come back at 11:20.
sounds good.
Cool. Okay. Just gonna share my screen for a second. Just one last little snippet on this. Just this would be what, like, if this is like a little visualization of like a 4-bit computer, like how it might look, like sending instruction by instruction through a very, very simple CPU. So yeah, you're just with this, with the 4-bit, you would send like 4 bits at a time. So 0011 or whatever. But those 0011s, that corresponds to like electricity or not. And then whether or not it has electricity, it goes through like all of these different circuits and all these different gates and chooses different patterns based on like whether or not there's electricity or not. And like you can perform operations, and you can like in your code, you can have like different instructions. I don't know if you like look at this, it's kind of like interesting to like look at this code simple instructions. It's like you can like load stuff, you can do addition and subtraction. There's like this computer just pretty much adds and subtracts, and then you do like and or not. It's kind of like computers, like if you look at like a process, like how the processors work and how they like handle like this whole dealing with electricity or not, it is really like it's and or and not. It like computers are built on like these 3 or 4 things, and or XOR not. It's really, really crazy how simple it is, but then with this simplicity, you build like crazy structures like this. And it's just like electricity going through a whole bunch of like, do you have electricity? Yes or no? And it's all these like complicated Boolean logic. So fun stuff there. Well, let's get away from that. Oh, well, since we saw it, who knows what? So we've seen and, both things have to be true. We saw or, one of the things have to be true, and not is, negates it. There's another one called a exclusive or, which we don't really use in programming too often, but there is like an exclusive or. Does anyone know what like an exclusive or is? That's where it's like it's an or statement that's only one has to be true and one has to be false. So it's kind of this case where it's like true. You have one true and one false. That would be true. If both were true, that would be false.
When would you need that then if it's not really used?
It's used a lot in computer architecture. Like when you're building out like the circuits. I don't know why it's not used. I think it just doesn't. I think we can just write. You can come up with an exclusive or with and or not. Like you can create the logic to do it. I think it's just so common at the low level. But I guess in code, in coding, there's just not many. I don't know. Is there not that many use cases? I can't really like. One I could think of is like a real world example of like an exclusive or is like, like biological parents. You need like a male and a female. You can't have like a male and a male, and you can't have a female and a female. You have to have like a male and a female. I don't know. Can you have a female and a female? Is that possible?
Well,
Anyway,
kind of.
what?
Well, kind of like they do that kind of to just take it, but not like, I mean, they have to do it in like a lab thing or thing.
Yeah.
Not like,
Well, isn't that just an and statement?
It's, but I mean, I could say like, it's once again, like breaking stuff in. I could say like a male is 0 and female is 1. And then to have like a child, you can't have a 0-0 combination. You can't have a 1-1 combination. You have to have a 0-1 combination. So that's like the exclusive or. It's like, but yeah, you could do that with an and state. You could be like, if male and female. I think that's why we don't use it in coding, because we can write it, probably like write it that makes even more sense. But when you're talking about computer architecture and you're talking about like the flow of electricity, I think the exclusive or comes up quite a bit. So they have a specific operation for that. So anyway. Yeah, well, let's get into, yeah, can they, I bet you probably, if you do have 2 females, you probably can have a baby, right? With like the help of a lab.
yeah, I've had people look into that kind of thing. I didn't really look into it myself, but they were looking into.
Has anyone actually ever, like has any human ever done that? Wonder.
I just know there was something for them to look into about having both of the guys. I don't know.
Wouldn't you have to change like genetic hormones? Like you'd have to like genetically modify that person, wouldn't you?
Well, you couldn't have a,
Or are you saying like they would, like the lab would do it? They would like take the DNA from those 2 people.
it's more like sci-fi. I mean, like 2 women couldn't have a male because like chromosomes, but
Yeah.
anyway. All right, I digress. Okay, let's go into SQL. So a couple things we're going to do for this. We can like do SQL stuff in terminal, which would be god awful to do. So there's some database tools specifically for Postgres that we can use. There's a couple different options. We're going to use, and we're going to download this one. It's called SQL. I don't even know how to say this. SQL Electron, SQL Electron. Sorry, I don't know how they pronounce it. Oh yeah, and with SQL, you can call it SQL or you can call it SQL. So let's go ahead and get started. Yeah, so yeah, SQL stands for Structured Query Language. And we're going to see what this just means. It's kind of like this language that makes it easy to talk to database. And SQL is actually it's structured. When we write a SQL command, it's going to read a lot like just you would say it in English. So it's this very organized language to query a database. There's different kinds of versions of SQL. It's kind of like having different programming language. There's SQLite, there's MySQL, there's Postgres, Oracle, SQL Server, but they're not going to be as different as say like Ruby and JavaScript are. They're going to be more similar because they all support kind of the SQL language standard. So they're going to be a little different in how they implement it, but they're fairly similar. So we're going to use this SQL Electron. I don't know how they say this. Anyway, this is a desktop app. So you're going to, I would just say download the graphical user interface. I already have this. Oh, wait, which one? Okay, so this takes you actually to their GitHub.
And then
What-
we use Postgres, right? So that's kind of already us using SQL.
Yeah, so this is going to be work very nicely with PostgreSQL. So this is why we're using this one. So sorry, I didn't realize this takes you to this GitHub page. So you're going to want to do the 1.371 DMG. See if I can open that in a new link. I don't know if I can Slack out this link. You can see their code. Let's just look there. Here's their website. Here's their GUI. It's on GitHub. Stories, components. Let's see if I want to actually see something here. See how this is just written in JavaScript? These are all these are TS files, they're just TypeScript files. I want to see if there's any like React stuff. So SQL this is kind of interesting because this is a desktop app written in JavaScript. So we can use this language called Electron to write native apps in JavaScript, so desktop apps. And it's actually, we can use, I'm trying to see if I can find any like React components, 'cause I'm sure they're in here. We can actually use React to write, desktop apps, which is pretty cool. And we're not going to use SQL Electron Electron, but we are going to use React Native. So React Native is a way to use React to write mobile apps.
Hey, James, real fast. Mine isn't opening. It says it can't be verified. And I don't know how to force
Yeah,
it.
same with me.
Will you share your screen and I'll kind of show you how to get around this for
Yeah.
someone?
It might just be a little loud. I have my kid right here with me, so.
Okay, so what you want to do is, go ahead and hit cancel. And then can you say open anyway on this? Yeah. So click open anyway. Click open. Is that not opening it?
It's jumping right now at the bottom bar, so. Do I need to click on it again? Or?
Yeah, see if you can click on it now. Yep, there you go. So you might have to allow it. Sometimes if you like right click on the package and you just right click and say open, it will do it. But did you open up that privacy thing or was that automatically opened up?
When it popped up the message that said move to trash or whatever, there was a question mark. I clicked on that and it popped up that little window to the left. And then I could open up the control panel from there, which was over here.
Yeah, okay.
Or you can just go to the control panel and your security and privacy, and it should take you to the same place.
Yeah. So yeah, you just either go to that security privacy panel, say open anyway. And that should allow you to open it. Does anyone else having issues still? Because you can share your screen and we can walk through it again.
I'm just trying to find where to approve it.
Do you want to here share your screen?
Yeah.
Because I'm sure other people are having the same issue. Okay,
Okay.
so go ahead.
Sorry.
Yeah, hit cancel.
Okay.
So go to security and privacy. It's in the system preferences, kind of middle right. We can, yes. Security and privacy. It's that, it's that one right there. All right. Go to general. Is it not popping up there? Click on the general tab. Okay. Yeah, now you need to click on the lock to make the,
I see
so
that.
the bottom lock. Click on that. Enter your password to, you know, whatever you use to log in. And then say open anyway. And then open.
Okay.
Cool.
Sweet.
Anyone else?
Yeah. So yeah, I don't. Was it? We were supposed to click on this. Click on this one. Oh, sorry.
Yeah.
You can't
I-
just see my screen.
I do it all the time.
Okay, so click on which one?
Yeah, so click on the
This one?
DMG. Yeah,
That one. Okay, that's what I clicked on because I was clicking on the other ones. When I clicked up here, nothing was happening.
yeah.
And then it
Well,
came-
then yeah, so click on the DMG one
Okay,
and then you download it.
and I don't see where that went though.
Yeah, it's right there at the very bottom. See, click on the disk
Okay, and then
and
just
then move it to your applications folder. And then, yeah, if you try to open this up, actually, if you go to your desktop and do a right click and do open, let's see if that bypasses. Sometimes that like bypasses the check.
nothing.
Okay, just, what? Okay, double click on it. Why is that not opening? Go to your, so in your computer where it says go on the top bar, like
Where does
top leftish,
top
it
left?
says go on your toolbar.
Oh,
Go, click on applications. Yeah, find SQL Electron. So scroll down. Should be in there. Yeah, right click here, open. Yeah, so hit cancel. So yeah, now, oh, it's right there, system preferences. You can just go there.
where?
On the right, system preferences in your applications. Down.
Oh,
middle.
this one. Okay.
Now go to security and privacy. It's the one that has the house to the right. Yep. And then go to yeah. Click to make the changes. Then go to the general tab. And say, yeah, open anyway.
With this collected.
Yeah. So it's,
Okay.
go ahead and click open. And then that should work.
But
Yeah, Mac just like has it, like if you don't download it from their app store, they're like, are you sure you want to open this?
then I can just now I can click it and it
Yeah,
should open.
yeah. And now it should work. And actually, why don't you just leave your screen shared? Because I kind of want to show how to set this up.
Okay.
Because I'm going to be all set up anyway. Actually, so go. Wait, will you make that small again? Was there more options when it was smaller? Like minimize this? No, okay, so go to, click on settings. Or we might want to do add. Let's see, okay. Okay, close out of this. Not, Can you not just close it?
I guess not. Now how do I open it?
Just click, should be, just double click on it. Is it not there? Or just do a new window. All right, so here's how we're gonna, okay, so click on add. All right, so for the name, you can just kind of call this whatever, just call this, I don't know, server, my server or something. What's important is, so go to the database type. And everyone should be doing this. So select PostgreSQL. And then for the host, or sorry, the server address, put in localhost. And no space, don't do it uppercase either, just localhost. Lowercase l. I don't know. Okay. Hit test. So hit that blue button, test. Okay. So if you see the screen thing, that means you set up the stuff right. So scroll down. I think now hit save. And there you go. So now you have this spot where you can now like go click on my server and like to connect. Cool. And notice on your left-hand side, what do those kind of look like?
That looks like my GitHub.
Your GitHub? Well, it's like it's your databases.
Files
From,
in
The
the database.
databases. Okay.
there's your
Oh,
databases.
yeah, that's more than what's in my GitHub. Yeah.
Yeah, so those are like whenever you did a Rails project, it's more when you did a Rails DB create, that's creating your databases. And now you can actually go access your databases. So this is a way we can actually now go in. We haven't been able to really do this yet without like the Rails console, but now we have a tool to go into like our databases in our Rails project. And now we can start actually typing SQL with these. So cool. So you're good. You can stop sharing here. Is anyone else having issues with this?
What was it that you put in the ad? I missed that.
So you can share your screen.
Uh-oh, I only have one computer on.
Oh, that's fine. So you just give it some name. You can call it whatever, like server, my server. And then for the database type, there should be a drop down. You do the PostgreSQL. And then for was it the name or the address? The address, it's the one where you give it under the name. I think it's address, right?
The server address.
Yeah. For that one, you do localhost.
Okay.
And then hit the test button just to make sure it's like this works. And then you can save it. And I can share I can actually do this because I can create another one. Why is that not? So yeah, I click add, some name, Postgres, localhost, test, and then save. You don't need to have two of them. Delete this. Cool. All right. So I think, does anyone not up to this point? where you can connect. Because we're going to use this to like, yeah, to start doing some database stuff. So I'm not going to connect to any of these. I just have this, it just says like Postgres1, but in here I can start typing some SQL. So we just maybe just some very basic commands. I'll just select these out and then I'll just comment and paste them in here as well. So there's going to be some basic, and just like I did with like VS Code, I can like highlight all of these and do a command / and it will comment them out. So I can do comments in SQL. And then I'm also just going to slack out this basic data terminology. Okay.
I didn't get it. It's not like working. Could I share my screen now? I have it.
Yeah, go for it.
Okay, sorry.
Oh, you're fine. Lovely setup. Okay. Yeah, go ahead, click add. Just give it some name. And then the database type. Oh yeah, do localhost and then database, do Postgres. Just click test. Cool. Now click save. What?
I think it's because she's searching for my server, but she named it Sharia.
Oh yeah, oh yeah, okay. You have in your search box, you have a search in there. So delete that search.
Oh my goodness. All right. That makes sense.
Good eye, Joe.
Well, now you have 3.
Yep, now I got
You can,
awesome.
yeah, you can click on the pencil on those other 2 and just remove 2 of them.
Okay, cool.
You don't need 3 of them.
Thank you.
Thank you, Joe. I would have not seen that.
That was fun.
All right. Cool. So yeah, let's just very briefly, just some very basic terminology. So database, this is the term describing the whole server, the whole database server. So it's going to be a collection of all of our tables. So what's a table? A table is a container that, is stored inside of our server, and our data has many rows. I really like to think of like the table as just like one Excel spreadsheet. And our database is composed of many Excel spreadsheets. And then the row is would be one like entry. It'd be like one thing in our table. Like if we had a person table, a row would be one person. We have a column. A column would be like, if we had a person table, a column would be an attribute about, the people, like age or name or ID. So think about row as like an entry into our table, and a column as like a description about our table. We have primary key. We know this is that unique identifier where we can grab any entry from our table. Not null. We've seen this. This means there's sometimes we can have values in our database that have to have a value. We have unique. Unique means that a value inside of a column cannot match any of the others. So like an ID is unique. If I have a person who has ID 1, I shouldn't see another person in that table, not the database, but the table who has that same ID. And default is how we can give like default values to the column of a row.
You can almost think of table as like each project.
Not like a project. Each project has their own database. And then a database could have many like, and don't get this like, I mean, you could do like it has many, but so each project's going to have one database, the way we're doing it. And then databases are going to be composed of many, like one to many tables. Like with our doctor's appointment, like with the appointments assignment we did, that's one database. And then there's like a doctor's table, there's an appointments table, there was a patient's table, etc. So, like I said, and I like to think about it to be like Excel spreadsheets. And then like in the Excel spreadsheets would be all of our, like I have Dr. ID 1, whose name is John, and he's a heart doctor, etc. All right. So with SQL, we have some, here are kind of the basic commands. We have a select command. So this is how we're going to extract data from our database. And we're going to go over all of these. We have an update. This is how we update data into our database. We have a delete. This is how we delete. We have an insert into. This is how we're going to add stuff into our database. Create. I mean, these are pretty like specific, right? These are the commands. They're very descriptive. It's kind of funny, like having, like saying what these do, because the name says what they do, right? What do you think create database does? Creates a new database. Create table, creates a new table. So this is where like SQL, that's why they call it like structured. It has a very structured language. It makes sense. So let's go create a database. So now we're not doing like has nothing to do with Rails. We're just gonna create a database. So we can do that. I'm gonna delete these for now, but those are out in Slack. So I want to create a database. So here's the command, create database. Now, SQL is not case sensitive, but it's kind of convention. To write, SQL commands, uppercase. Ship. I wonder if I do have a dealership database already. I'm just going to delete this one. Or drop. This is how I drop it. Drop. Okay. I already had one, so I just dropped it. So I'm going to create database dealership. So I click execute. And now I get the screen like query executed successfully. And if I were to go scroll down, now I have, and you should see this, I have like this dealership database. Cool. So the next command we're going to do is create table. So create table looks something like this. Create table and then the name of the table, and then in parentheses, give it the column, the data type, and constraint.
Do we want to do this in the Postgres one or the dealership one?
You can do this in here.
Okay.
I'm pretty sure we'll find out right here. So what I'm going to do now, so let's actually, so I have this. So let's just kind of think about how would we do this in like Rails? How do we create like a database called dealership? or like, what would kind of be the command that would do this? This would actually be like the Rails G or Rails new, dealership. Etc. Like obviously this is doing a lot more, but, and then we would come in here and do a Rails. Like doing these two things with behind the scenes, eventually it does a lot more, but it would eventually create this database called dealership. Technically with the Rails, it'd be like, development, but does that make sense? So we're skipping the Rails part and just doing the SQL part. So let's create a table now. So I'm going to do this create, kind of following this convention table. So we're going to have a table, and tables are spelled like we do them plural. So I'm going to have a cars table. And, I'm going to have an ID. So now I do need to like say this, hey, this is going to have an ID. I'm going to say this is serial and this is a primary key. And then I separate these by commas. And then I'd have a make. So make is going to be a var char. So now we have like this different type of data. It's called a var char, stands for varying character. So kind of going back to like, why would we have big ints and small ints? It's kind of like, well, might take up less storage. Database, this is the level where we kind of might care about storage. So what I'm saying here is I don't this is a character. I could kind of think of the like a varchar is kind of like a string, but then I can kind of say, hey, like I want it might vary in length, but I don't really expect my make to be greater than 50 characters. So it's like a string who I would not expect to be greater than 50. And then I could say something like, hey, this cannot be null. So I'm putting a constraint, get on like a validation almost that like, hey, you need to give me a make. I could do a model. So all the like the stuff I'm doing in caps lock, it doesn't have to be, but it's kind of just letting me know, hey, this is like the SQL part of this. These are all like SQL instructions. And then I could have a year, integer. Once again, we'll just have these all be not null. And then color, varchar. Maybe I don't expect that to be greater than like 25 characters. That could be not null. And then what else? Let's do mileage. That could be an integer. Not null. And let's do a runs. And for this one, I could have this be like a Boolean. And I could give it a default value of true. So if someone doesn't give me a value, I'm just going to default this for like whenever anyone creates one, if they don't give me this, I'll default it to true. And with SQL, we can do a semicolon, which would say, hey, this is like the end of like the statement or the query. I can also like highlight this and now I can run. Relation cars already. Oh, did I not delete this? Saying the relationship already exists. Okay, let me try this again. This is kind of like that error you would maybe see like, hey, it's like this table or like this.
Why do you highlight it first?
It's something with like SQL Electron. If I just highlight it, it will just like run the one command.
Oh.
I don't, if I only have one command in here, I don't have to highlight it.
They create a new database called dealership if you forgot to highlight it. Like,
Yeah, I
because
should-
in the top, it's, at least in mine, it still says create database dealership.
Yeah, I shouldn't have it. So if I drop it, I thought I dropped it because if I look for dealership, I don't have it. I might need to connect. Let's try this one more time because it's not there. I can do a db create or like I never, this is like the only time I create databases is for this lecture, create database dealership. Execute. Okay, so that's there. Oh, did I, maybe I did, I see what you're saying. I ran this twice, maybe. Okay, now let's run that. No, did I type something wrong here? Let's see, maybe I do need to connect to this one. Okay, I'm gonna close out of here. No, it should just be here. Okay. Is anyone else getting this error?
Mine worked.
I'm getting the exact error.
What? Who else? So we have
Mine worked.
post.
What does it say if it worked? Mine just like cleared what I had.
You should have this green.
Oh, mine just, when I did it, mine just cleared what I had on the thing.
Clear. Oh, that it should clear this.
Yeah, that just went away.
That yeah, that shouldn't. That's like you deleted it.
Oh.
Unless it opened a new,
But I do, but it says dealership too now, so.
yeah, probably
Oh.
open a new tab or create a new database. Oh, did you
It
you have
worked, like,
that
Oh, it
create
opened a new
database?
spot.
She
Okay,
might have created
it-
another database.
it
It
worked.
opened, I don't know. I don't know if it did what it was supposed to, but it did something.
All right. I mean, I have it. The weird thing is, it's like I have it. Okay, so let's try this and then we'll see where people are at. So it's weird because like it says I already have it, and I was actually able to get it to work. So oh, except I just did that in my blog. That's why that worked. Yeah, I created this cars in my blog database, but if I'm in my dealership, what? Why can't I connect to this? It's like not letting me. All right, if this isn't working here's how I think I'm just gonna like, we can do this. Let's just pick one, just pick any of your databases, maybe pick one you don't care about. So it doesn't really matter, just test, that seems like one I don't care about. I'm gonna click on that. And I'm going to connect to this database. Cool. And then I'm going to create a table here. So I'll slack out this command. And that works. So I just connected to a database. And now I'm on this test.io development. You can, like I said, you can pick any one of yours that you don't, any one of your Rails projects you don't care about, just connect to it. And then we can go in there and we can create the table of cars. All right. So yeah, now that this is done, I don't need to like run this again. So I could either comment it out if you just want to have it for reference, or you could just delete it. Okay, so now I have like, but let's just ask this, like, if I were to, how would I do this in Rails? Like, what do I do in Rails that would kind of create this?
Creating a model.
Yeah, it'd be like Rails G model car, make model etc. And then also doing the Rails DB migrate. Like that would, I mean, that does a lot more things, but behind the scenes, that would eventually go in and like run this command, where it create this table called cars. Okay, so now let's go in and let's, I'm going to slack this out if you want to just copy and paste this, but we're going to now add something into our cars table. So I do an insert into cars. And then I'm going to tell it the order of the things I want to enter. So it's like make, model, color, because these are the attributes I have in my car table, year, mileage. And then I could do values, cheap. So that's going to be the make. I'm just kind of matching the order. So the model could be Wrangler. The color, whatever, blue. Year 2020. Mileage 1,000. So if I run this, we get the query executed successfully, affected rows. And I just kind of want to like show this, the semicolon. So this is, the semicolon is going to denote the end of like the call. Like I don't want to put the semicolon here because it's this whole, the SQL call is like both of these lines. So I could put it there and then that would denote the end of this. And I just ran this again twice. So now I'm probably going to have two of these Jeep Wranglers in here. But yeah, I could come in here and like add some more. Cool. All right. We could also, and I'll slack this one out because I don't want to type all this out. We could also do multiple inserts in the same line. I'll show you this. So I can say, insert into car, make, model, call, color, mileage, runs. I can use the default to say, hey, use the default value, or I can like actually go in and put the actual value. And in this one command, I could like add, 7 cars at the same time. And then it's saying, hey, how many rows were affected? 7, because I inserted 7 new entries into my table. So that's why I'm getting back this 7 rows affected. Cool. So now that we've actually added stuff, well, let's just try doing this. So since some of these could not be null, let's just see if we do like a make. That's a syntax error. It doesn't like that comma. So now I'm getting an error. Hey, like there's some stuff. I'm getting a null value in model. So I need, this is saying, hey, you can't create a car into this database because you don't have a model. Because we put that constraint, that model can't be null. So something like that wouldn't work. Okay, so let's talk about now, how do we grab stuff from the database? Well, this is going to be the select statement. So let's just do this, the select, we can say like, hey, column name separated by columns. And then from table name. That's kind of just like the general syntax. So I could do something like this. Select, make model from cars. And then end off the query with the semicolon, execute. And see, that gives me all the make and model data from my cars table. I could also do a bang, select star. Star just means everything from cars. I don't have to have these on new lines. It can kind of be like a readability thing. If I want to have my queries to have them separated on different lines, but run this. So where is it? Well, I'm actually running 2 queries right now. I have this one separated, but like in the semicolon saying, hey, this query's done. And then I have this one. So if I actually scroll down, there's my second query. So I can comment out this one. And there we go. So that grabs everything from that cars model, it grabs all of the columns. Right, this would be like a car.all in Rails. Yeah, we can get specific with SQL. We can definitely go in and like be very exact, say exactly what we want. So maybe I just want the make, model, year, and mileage. Let's maybe just grab the ID too. All right. I can also, maybe I want some, I only want to grab certain types of things. Maybe I only want the car where cars.mileage is less than, 50,000. Because maybe I don't want like cars with a lot of mileage. So I can use the where statement, like the where clause. So now I can do queries where I'm only grabbing, certain things. I can also combine these with like and statements. an or not. So I can do and. Let's do like car dot make, equals. Right, this is very readable. Select ID, make, model year, mileage from cars where car dot mileage is less than 50,000 and car dot make equals Jeep. I have a syntax errors. Oh, so I'm selecting from cars. So I need when I do this where cars dot mileage, car dot make, that needs to be cars. So now that's just going to give me back those items that match that clause. I could do a or statement. Maybe I just really like Jeeps or cars that are under 50,000. So there's a Jeep, that has greater than 50,000. So. And then I could do like maybe I don't like Jeeps. I could do a not statement. Actually, that's kind of weird because that's going to grab any car that has less than 50,000 miles or it's not a Jeep. So my Jeeps should have less than 50,000 miles. And then grab any other make. Don't care about the mileage. But that's the same, the or not, and those are going to work the same. So by default, these are always going to come back by ID, but maybe, I want them ordered by mileage. So I could use the order by command. Order by cars dot mileage. And that's going to give me like from low to high, or I could say, hey, get those to me descending. And then that will go from high to low. So just some basic, selecting, we can select specific columns from specific tables. We can kind of filter results with the where clause. And then we can order by certain columns. So SQL is like we can definitely do a lot of stuff, get back data exactly how we want it. So let's go ahead and talk about, and there's ways to do, like we're going to see with Rails, we can do this type of stuff. We can order by, actually wouldn't be that hard. There's like the method's going to be very similar in Rails. All right, let's do update. So update's going to have this syntax. So update, so we'll say update, then the table name, and then we'll kind of set the values. So let's look at this. So let's say I want to go update cars. So there's my table, and I'm going to set, and let's do runs, or let's do actually mileage. So like really visible, like let's set mileage to equal like 1, 2, 3, 4, 5. Now, if I were to run this command, this would go through and change all of my cars' mileages to 1, 2, 3, 4, 5. Probably don't want to do that. Maybe I do, but I can also, what I probably want to do is like do a where clause and, do like cars.id equal 1. So here's my Jeep, has ID 1, it has 1,000 miles. Let's go ahead and run this. And then I can maybe like select down here just so we can see it. See if that changed or not. I could do a select star from cars. And there's actually, it looks like it's giving us, it doesn't give us back by ID. It looks like it's giving us it back by like when it was updated. So there's my Jeep with ID 1, and now it has 1, 2, 3, 4, 5 miles. And look, yeah, this was lowercase. I could do a mix and match. It's still gonna work. Doesn't care about, it's case insensitive. But if I'm being conventional, sometimes that can be a convention just to do all your SQL commands uppercase. All right, let's do a delete. So delete's going to be very similar to our update. We just don't have this set. So just delete cars. We don't need a clause. I say delete cars, I would delete everything, but so we probably want a clause on here, right? So let's go ahead and delete where cars equals 1. And then I'll also just run this command after. What doesn't it like? Near cars, delete. Oh, delete from, I need a from here. And now, so I delete from my cars table where the cars ID equals 1, and now it's gone. Cool. I'm gonna select this part out. So when we select stuff, and this is out in Slack, there's the like command. Oh man, oop, okay. I just deleted. Oh, I think this might have what you might have done, Catherine, is hit the discard. I think that deletes everything instead of the execute.
Well, so when I didn't think about looking at a second tab, there was, I actually made
Oh,
a second tab and moved me over to there where there was nothing. So I went back to Postgres and it was still there.
okay, cool.
But yeah.
Because I just hit the discard and that just deleted everything. But all right. So let's look at some more like selecting stuff. The like operator is used in a where clause to search for specific patterns and columns. So there's kind of 2 wildcards we can use with this. There's the %. This is going to represent like 0, 1, or more. And then the underscore is going to represent a single character. So let's see what this kind of looks like. This is where we can kind of be a little more select, like, or loose in what we get back. Instead of saying, hey, just find Jeep, we can find things that look like Jeep or something. So let me show you what this means. So let's do select star cars, where cars.make is like. So what I can do, I can say J %. So what this is saying, go find all the makes where the J looks like, where the car.make looks like this. Essentially, it starts with a J and then it can have 0, 1, or multiple characters after that J. So it's essentially saying it just starts with a J. So that gives us our Jeep and Jaguar. Now, if I did, GE, that gets rid of the Jaguar because the Jaguar has an A. The underscore, or let's do this. Let's say, I forget what kind of cars we have in here. Let's do this, what would this kind of say? That's,
Ends with a
Ends
P.
with a P.
yeah, ends with the P. Do we have one? I forget. Do we have one? Do we have multiple that like end with an R? I don't know. But okay, so let's look at the other one. So we could do that. So the underscore represents a single character. So where it's like J underscore underscore underscore, that gives us our Jeeps because it's like, hey, it's a J and then it has 3 characters. If I just did J and then 2 characters, that doesn't match anything. So that's what we can do like that. We could do a where cars.make, we can do a in. So this is where we could give it like a list. I could say, hey, is it a Jeep? It's kind of like a shorthand of an or. Is it in this list? But this can be nice if we have like a arrays of stuff or Toyota. Now this one, it is going to match the case sensitivity of those strings. So this was uppercase. So it's not going to match that because my Jeeps in my database are like, that's case sensitive. There's like a, so you're going to go through a lot of these in the homework. So there's a lot of these commands where you can really get like specific. But what I want to spend the rest of the class on, and we'll take a break before this, is the joins. But where is my error? So I can do it between. Where is the error? These can sometimes be hard to, oh, sorry, between and. So give me all the cars where the mileage is between this range. One quick other thing, I can alias this cars table as like a different name. Maybe I'm getting sick of typing cars. I can alias this as C. So this is aliasing my table. Works the same. I can alias a column. So now it's going to like, this would change the column name as it comes back from data. And I can look at like, oh, here's the JSON. Or I copied it. It actually changes how it comes back if I alias the column. But let's take a break. Let's come back. I want to spend the last like 20 minutes before lunch on joins. And yeah, you're going to go through all of this through the homework. So but let's take a break. We'll come back at 12:40 and then we'll spend the rest of the time talking about joins. Cool. Okay. Let's see here. We've got just about 20 minutes to kind of go through this, and you're going to have all the homework is pretty good. I think this is the better way to learn it, is just going through and typing this out yourself, which you'll be able to do in the homework. But one thing I do want to spend just some time on before we head out to lunch is the join statement, because this one's pretty important. We use it a lot. So something that happens with our databases is we don't just have one or two tables. We have a lot of tables, but then we're going to want to do queries that access different parts from different tables. So we're going to need to like join these queries together. So I'm trying to slack out this. Man, I sometimes hate Neo. I want to just slack out this SQL command really quick. Okay. All right, so let's go ahead and I'm going to share my screen and let's look at what I just slacked out, because this is going to be SQL command. So we are creating another table called parts. But there's one kind of important part about this. And this is right here. This car underscore ID, which is an integer, and this references. What do you think this is doing, or what do you think is what this is? So we have a parts, we're creating a parts table that has like ID, name, description, serial number, broken. What about this?
Is that just creating IDs?
Yeah, this is going to be our foreign key. So we're kind of right here, we're creating this in the Rails. This would be like the Rails G model part, car to. And really with all that's doing behind the scenes is we're just adding a car ID column to our parts table. It's going to be an integer and it's going to reference the cars table. So this is saying, hey, this car ID is going to be the foreign key. And then we can come in here and we can, we actually do a select statement, select ID from cars, order by random, limit 1. So this actually selects an ID from our cars table. It orders them it just randomly orders them, but then we only limit 1. So this is how we can just get back an ID from our cars. Select floor. Here we're doing the, we're just kind of doing a serial number, doing a random number. We're kind of like we did in JavaScript, where we floor it and then we times it by a number. It should give us probably a number from 0 up to this number. But the important part here, yeah, we have this car ID, references cars, and then we're using SQL itself to grab an actual valid ID of a car. So now we can go ahead and execute. Well, what is wrong with this? Okay. So it affected 4 rows because we created 4 parts. So now I can do like select star parts. And there we go. So now I have a, rim and tires that belongs to car ID 8. So before we get into the join statement, I just want to look at this visually. And I threw this out in Slack, this link. Some kind of two different kind of joins, or like the kinds of joins we're going to have. So let's just look at these. Because when you talk about joins, you'll kind of see these Venn diagrams. And I think they can be a little confusing, especially when you're just first kind of using them. But let's just kind of look at what they are. So we have an inner join. This one's going to probably be the most used one that we'll use the most. And this is like where we're going to match when we're going to match when the condition is met on both, and we're going to get back non-null values. And it's like, what the hell does that mean? There's a left join where it's like, we'll join when, if we do a left join, we're going to match the left table whose values can be null or not null, or the right join. I mean, I think when you just look at these diagrams, it's like, it doesn't make any sense. The way to visualize it is, I think this can really, like, this website helps a lot. So we're going to do a inner join on this. And it's what this is saying. We have two tables. We have like a Facebook table and a LinkedIn table. And we're going to join on a condition. So we select star from Facebook, join LinkedIn. This is the like syntax of a join statement. And then we're going to do this on a condition. So we're joining where the Facebook name equals the LinkedIn name. So this is where the different types of joins come in, is on this on statement. So let's just look at the inner join. So this is going to match when both of them are in both tables. So when it's equal. So what that means is if I do an inner join, it's only going to join it if, you know, the name is in both tables. So Matt is on both tables. Lisa is in both tables. Jeff is not, but Sarah is in both tables and Lewis is not. So when I select star from Facebook and LinkedIn, what this is going to do, it kind of goes through, and you can kind of visualize this. It's like, hey, does Matt match any of those? Nope. Does Lisa? Yes. Then let's add those. And notice how the join is giving me back both the Facebook name and the Facebook number of friends, the LinkedIn name and the LinkedIn number of connections. So it's taking these two tables and joining them together into like this mixed data set. But on the inner join, it's only going to match where the values have to be, like it's on that on statement, it will match both of them. So I'll get Matt. So since Matt's in both of them, it will grab both of those pieces of data. That's one row. Lisa's in both of them. So Matt, throw both of those in there, and Sarah's in there. So match both of them. Notice Jeff and Luis, they're not in both tables. So they're not included in this join. Does that, I think you kind of just have to do it a couple times and look at it. Let's look at the left join and right join. They're kind of like the same. They're just like inverses of each other. So if I do a left join, what I'm saying is give me back all the value, like all the things from the left join with the right, even if there's not a match, and give that back. So there's the case here that's different with the inner join. Notice that Jeff is not in the LinkedIn table. So we're doing a left join, you know, we're doing from Facebook left join with this one. So we're going to include Jeff in this one because we're going to grab back all of the things from the Facebook table. but there's not going to be a match for LinkedIn. So those values are going to be null. So Matt matches, so we'll grab Matt. Lisa will match, we'll grab back Lisa. Jeff doesn't match, but we still grab the Facebook data for Jeff. There's just no LinkedIn data. So we grab it anyway because we're doing a left join. If it was the difference between a left join, in this case, a left join and an inner join, is we wouldn't include Jeff in this one.
So if it was a right join, it would grab Luis instead of Jeff.
Yeah, so that, yeah, the right join. And you could really just like switch the order of these two. You could do a select from LinkedIn, left join Facebook, and that would do the same. So it's kind of redundant in a way, but yeah, we could do a right join. And like you said, that's going to give us Luis. So we're doing a select star from Facebook. Where's the left join? It doesn't actually say right join. It looks like a typo, but that, yeah, this is trying to, like, it's doing a right join. So Luis would go in there, but there's no Facebook name. And then there's the outer join, which would give us both Luis and Jeff. So Jeff doesn't match, but we'd still grab the Jeff data because Jeff does, you know, Jeff's in the database. There's just no LinkedIn name. And there we go. There's Luis. So that's just a way to like visualize these. But like I said, for what we're going to do, the one we're going to use the most is the inner join. So let's now go in and write an inner join statement. And we're going to be doing a lot of join statements this week. So we'll get some practice with these and we'll kind of go through that example again. So let's go ahead and do this. Okay, so let's come into our tables. So I'm going to want to grab and I'm just going to write this out first, and then we'll kind of look at it. I'm going to do p.name.
You're not sharing your screen.
Oop. Was I not sharing my screen that whole time?
No, you just stopped.
Oh, okay. I was hoping I showed this animation, right?
Yeah.
Okay. It's like good. Okay. All right. So yeah, let's go in and write a join statement. So I'm just going to write this down. So I'm going to do some aliasing here. I'm going to select p.name. This is really part.name. I'm going to call this as part_name. And let's just do c.make right now. So that's car.make. So I'm doing aliasing now because this will help like me read, is this from the part or car table, parts or cars table. So I'm going to do this from cars. But yeah, I could say cars.make, but I want to alias this. So I'm going to do as C. And then I'm going to do a inner join parts as P. So now that's why I'm doing like, I could do parts.name and not have this alias, or I could alias this and now I can just call this. Now I can refer to parts as P in my query. And then I need a on for my join. So my part has a car ID. So how I want to join this is my part car_ID equals the car.id. And let's also, this might help too if we do like a select star from cars and since I'm going to be doing multiple queries, I definitely need semicolons to end the queries. Select star parts. So I'm running 3 different queries so I can see my cars table, my parts table, and then I can see the result of this join. I have a syntax error. These are always a little tough to find. Near C, I'm forgetting a comma. Oh, on C.id. Okay, so here's my cars. There's my parts. And here's this. Might be a little hard to read. Maybe what I could do is in this query, let's grab sometimes you do have to alias, like I want to grab my ID. Let's actually, no, we don't. Let's just do my car.id and then my part.car_ID. So notice how like my car, this is the ID of the car in my car table, and this is the car_ID in my parts, and they're matching. So I have a Dodge, and we could actually grab the, part ID. This one I would have to alias because I can't have 2 IDs. Part ID. So this is part 1, but it belongs to car 8. This is part 2, belongs to car 2. Part 3 belongs to car 8, which is the Dodge. See, that's going to be this is going to be the car with ID 8. So this Dodge has this hood scoop and rims and tires. Now yours isn't going to like look the same because your query won't be the same because we kind of randomized what part is associated with what car. See, I could look at here, so I could look at my car ID 1. Oh, it's a car ID with ID 8. See, that is a Dodge Ram. Dodge. And then my part with ID 1, that's my hood scoop, whatever that is. That belongs to car 8. Like I could grab and this is where I can so I can just grab any of the columns I want from either table. So I could grab the mileage. Notice how these mileages, those are the same, right? Because it's the same car. They should have the same mileage. It's just it's just the part is different. Let's see if I'm not sure if this is going to change anything if I do a left join. See if we get any null values. Yeah. So now with the left, I'm getting, if I do a left join, I'm going to get all of my cars. But these cars don't have any parts associated with them. But there's all the car data anyway. If I do a right join, that's going to give me all my parts, even though if they're not associated with a car. But we don't have any parts that are not associated with the car. Because when I did my query, I made sure that I associated all my parts with the car. So there's going to be no null values here. But there would be if I do a left join, because I do have cars that don't have parts. Does that make sense? Kind of.
Yeah, that makes sense.
Yeah, somewhat, yeah. You just have to go through it a few times.
And we're going to do a lot of these joins. We can actually do multiple, like we can have multiple tables. We can join multiple tables. But we'll look at that.
So basically the whole point to SQL is just finding things in your database, right? Is there anything we're going to be using this for that's more, I don't know, more functional? Like I just want to know, is this just for finding things in the database, or is this kind of just intro into?
Yeah, I mean, we did see we could add and update.
Yeah.
Delete stuff. But yeah, SQL is largely going to be, especially with how we're using it, it's going to be finding stuff. And it really does become like, I think the big, like, yeah, finding stuff and joining, because when you get to like bigger databases, they're going to have like tons of tables that are like associated, because it's like an efficient, like it's all about like efficiently storing data, not like storing duplicate data. So yeah, then our queries get a little more complicated and like, grabbing different parts from different tables. So, and yeah, I would say it is, I mean, you can do stuff like, we can do like functional stuff, and we'll see like stuff like that where, we could like, with SQL, we could like find the average mileage of our cars. So we could go through and like, we could count up how many cars we have. We could like sum up all the mileage and get the average. So there's like functional stuff like that we could do.
But basically it's just a tool to help you understand your database better, especially when it's like you don't understand the database because it's someone else's.
Yeah, it's definitely a tool to like, very powerful tool to like, yeah, interact with your database.
Okay, that makes more sense.
So. Who was it? Jess, what kind of things would you do with SQL?
Well, we had like a bunch of different databases, so a lot of times I was joining on like 4 or 5 different tables and just pulling a lot, because I was working for a laboratory, so we were pulling like test results, or like we do a lot of pathologists like QA, so all the cases that they worked on and things like that, and extrapolate numbers from that.
It's a lot. Yeah, a lot of stuff you can do, right? It's powerful language. This is just data. But yeah, you'll get some practice with it. You'll see. Let me just go over the homework really quick. It's not going to be anything you really turn in anyway, but it's called this SQL bolt. And this will just be like individual, kind of like on your honor type deal, because you don't really turn it in, but it's a nice little like interactive intro into SQL. So you go through and like it gives you like these little lessons, so you can read up on it on these little sections, and then it gives you little challenges. So you want to find the title of each film. Well, in this section's on select, so hopefully if there's a section that's a little confusing, you could go through and find the answer or something helpful. So it's like find the title. So I do select title. I can spell title right. And then like it automatically like checks that off. Okay, now I want to find the director. Title and director, okay. Title and year.
You said SQL is used to find things in your database?
It's just used to interact. You can find it, you can add stuff, you can delete stuff. You can, yeah.
So almost just like another way of doing CRUD.
Can definitely do all, yeah, do CRUD. I mean, we've been like using, like Rails has been doing the SQL for us. Like when we do like a movie.all in Rails, it behind the scenes is going to be like doing a SQL call like this, select star from movies. Like Rails is just a nice language. It's like, well, we're not going to make you write SQL all the time. Yeah. So this will be the homework. So it definitely gets a little more in depth and a little more complicated, but it's nice because it just kind of goes step by step. And so yeah, there's about 18 lessons. And that will be your homework. Cool.
Sounds good.
Well, sweet. Let's hop off. We can come back at 12 or 2:10. And yeah, let's go from there. I think this is a little bit of a breather, I'd feel like, as far as homework. So
Cool.
cool. Let's
Thank you.
Yeah.
Thank you.
Have a good lunch, everyone.
You
Too.
too.
Thank you.